and then we're going to move on to a little bit of calculus review just to get us back in the swing of things. Next class we'll deal more with modeling, but we'll do a little bit of intro today. Okay, so what is a differential equation? It is an equation that includes one or more derivatives in it. A solution to a differential equation is a function. So this is something that feels different. It takes some getting used to. Typically, when you've solved equations in your mathematical past, the solution has been a number, right? It's a number that makes the equation true. The solution to a differential equation is a function that makes the equation true. Okay. So for example, what function could make this differential equation true? What function makes it so that its derivative is the sine of x plus 2? Negative cosine of x plus 2x. So my solution is a function, y equals negative cosine x plus 2x. Because if I were to take the derivative of this, dy dx would be sine x plus 2. Does that make sense? Okay. So solutions are functions. And there's actually more than one solution. This is one. Could anybody give me another solution to this differential equation? Yeah, you could throw any constant on the end, right? Because when you take the derivative of that constant, it will just become a 0, and you would still get the same derivative. So it turns out there's actually a whole family of functions that satisfies this differential equation. So the general solution is when you throw the plus c on there. A specific solution is if you choose a value of c. If I want to obtain a unique solution, you need an initial value, right? So if I want to know what the value of c has to be, you need more information. So for example, same differential equation, dy dx is sine of x plus 2. But I want to find the particular solution so that y of 3 equals 5. And this is called an initial value problem, when you have a differential equation and an initial value. So how would I use that initial value to figure out what c is? Plug in 3 for x, set it equal to 5. So y of 3 would be negative cosine of 3 plus 6 plus c equals 5. And then you solve for the c. So c is going to be negative 1 cosine of 3 minus 1. So my specific solution is the function. It's very tempting to just circle that because you finished solving for a number. But the solution to the initial value problem is the function. Where you replace the c with the value that you solved for. All right, so using a little bit of calculus that we remember from Calc 1 and 2, we were able to solve this differential equation, dy dx equals the sine of x plus 2. There are many analytic techniques for finding a solution to a differential equation. We'll study lots of them over the course of the semester. But before you can actually find a solution, just like when you first started solving equations where numbers were the unknown, you have to be able to test if you have a candidate for a solution, test to see if it works, right? By plugging in and seeing if the equation's true. So that's what we're going to do here. I have a function, y equals x to the negative 3/2. I'm claiming that that is a solution, that function is a solution to this differential equation. That 4x squared plus y double prime plus 12xy prime plus 3y equals 0. So I'm claiming that this is a solution. So to check, I have to plug in all of the things in this formula and make sure that this equation actually does equal 0, that the two sides are actually equal. So I have a y, My equation involves y's, y primes, and y double primes. So I'm going to need the first two derivatives of the candidate solution. All right, what is y prime? Yep, -3/2 x to the -5/2. So that's our first derivative. And the second derivative? Yeah. Good. So now I'm going to take those two things, plug them into the equation, or three things, the y prime, and y double prime, plug them all into the equation, make sure that the two sides of the equation are actually equal. Okay, so I've got 4x squared, and then I have to plug in y double prime, which is 15/4 x to the -7/2. So 4x squared y double prime plus 12x, and then put in a y prime, -3/2 x to the -5/2, plus 3 times y, which is x to the -3/2. And I want to evaluate all that. Does it equal 0? If you simplify that whole mess on the left. Let's see. So it's just going to take a little bit of algebra. Here my 4's cancel. X squared times x to the -7/2, like bases, I can add the exponents. So 4/2 plus -7/2 is -3/2. So this is 15x to the -3/2. Did I do it right? Okay. All right, so over here, I can cancel those, put 6 there. So I've got -18 for my coefficient. And then x to the first times x to the -5/2 is x to the -3/2. And then I have plus 3x to the -3/2. Does that add up to 0? Yeah, those are all like terms now. And I have 0, x to the -3/2. That does, in fact, equal 0. So I've shown that that is a solution to the differential equation. When you plug it in, the equation is true. Yes.
You could then check to see if it's true for x greater.
Good question. So I have this restriction on the differential equation that x has to be positive. I think that I've shown it's true for all x, which means it's definitely true for positive x's. All right, so last part of today's demo is sort of what do we use differential equations for? Okay, so we know what it is. We know what the solutions are, their functions. We can check if a given function is a solution. If the equation is simple enough, we might be able to analytically come up with a solution. And then what are we going to use it for? So the process of describing a physical situation with a differential equation is called modeling. We'll be looking at modeling several times throughout this class. Some steps in the modeling process are state your underlying assumptions, identify the relevant variables and parameters, and then use your assumptions from step 1 to formulate an equation using the variables from step 2. All right, so here's the US population from 1800 to 2000 in a scatter plot. So the first kind of model we're going to study is called the Malthusian Model. And our assumption for the Malthusian Model is that the growth rate of a population is proportional to the size of the population. The more people there are in a population, the faster the population grows because there are more people reproducing. So what are my variables here? What are my important pieces of information if I was going to write a model for this? Population, we'll have that be P. Yeah, the way the population changes, which is, how can I represent the rate of change of a population? Still can hear you. Oh, close. Delta P, that's change in population, but I want to have with respect to time. Yeah, so how do I write that? A P with a dot over it is it stands for derivative. Yeah, so I could write P prime or a P with a dot over it or dp dt. I'm going to go with dp dt because I want to remind you that time is a variable in this formula. So dp dt is the rate of growth of the population, and we should just not forget that time is a variable. That's what we're trying to do, is model the size of this population over time. Okay, so I want to take this assumption, very simple assumption, very basic assumption, that a population grows faster as it gets bigger, that the growth rate is proportional to the size of the population. How can I translate that into an equation? Try to go like piece by piece. The growth rate of the population, that translates to dp dt. And then what does proportional mean? Multiplied by something. Yeah, so that thing, whatever it is, we don't know, we'll call it k. Some constant k times the size of the population, which is represented by the variable p. So this is the Malthusian model. It just says that the rate of growth is proportional to the population size. This is called a first order differential equation because it only contains first derivatives. The example we did a few minutes ago where we checked a solution, that was a second order. It had a second derivative in it. It's called an ordinary differential equation, often shorthand ODE, because it does not contain any partial derivatives, right? So you probably learned about partial derivatives if you took Calc 3. We won't be dealing with that in this class. It's only ODEs. All right, so let's confirm that the formula P of t equals 0, the function, the zero function, that's just a flat line, the x-axis, is a solution to the Malthusian model. Okay. So I'm just going to plug P of t into this equation and show that it is a solution, that equation is true. So if P of t equals 0, what's dp dt? 0. Okay, so now when I do my plug-in, right, here's my differential equation. dp dt is 0. Oops, that's supposed to be a p. Equals k times p, which is always 0. So 0 equals 0. It's a solution. Okay, so when I plug P of t equals 0 into that differential equation, the equation is true. P of t is a solution. So this is just a constant function. It's called an equilibrium solution. Any solution where the function is a constant, just some number, that's called an equilibrium solution. And in this case, it corresponds to a non-existent population. If there are no people, then the population can't grow or shrink. It just always stays the same. All right, so that's your intro. I'm going to have you work on some stuff in your groups / individually, whichever you're comfortable with. If you have questions, you can put the flag up and I'll come around and help.